Problem 50, page 360. A projectile of mass m moves to the right with a speed v initial. The projectile strikes and sticks to the end of a stationary rod of mass m and length d, pivoted about a frictionless axle through its center, O. Find the angular speed of the system right after the collision. So A, we have to find omega just after the collision. Here is the initial state. This is before the collision. And here at the final state, just after the collision. You know here, we have to apply the conservation of angular momentum. The summation of tau external equals to dl divided by dt. Okay? You know here the total force applied on the system. Here we have mg, and here we have the reaction n. You know tau of mg equals to tau of n equals to 0. Why? Because they pass through the center or the axle. So we can say here pass through the axle. In this case, the summation of tau equals to O. So L must be constant. L constant, it means L initial must be L final. L initial, it's just before collision. L final is just after collision. Okay? You know, in general, L must be equal to R cross P. Or we can say equals to R cross M V. Okay, here for the mass M, we have a translational motion. You know, L initial is equal only to the L initial of the mass M. Okay, equals to L initial of the mass M, and L initial of the rod equals to 0 because it was at rest. We don't have velocity. So here we can write directly. Here we have R times M times V initial. Okay, you know R is the projection from the center O to the velocity. Here we have the velocity. We have to elongate the velocity, and here we have the projection from the axis, from the axle to the velocity. This one is R, which has a length equals to d divided by 2. So we can write here d divided by 2 times m times v initial. This is the magnitude of L initial. What about L final? L final, as you know here, just after the collision. We have omega, and you have a pure rotational motion. In the case of pure rotation, we can write directly I of the system times omega. You know, I of the system equals to I of the ball plus I of the rod times omega. We can calculate here, you know, I of the ball equals to 0. Why? Because ICM of the ball equal to 0. The axis is not passing through the ball. In this case, we don't have ICM. Plus M times the distance between the center of mass of the ball and the axis, which is equal to D divided by 2 square. What about I of the rod, which is equal to ICM of the rod plus M times the distance between the center of mass of the rod and the axis equal to 0. So we have only ICM. It must be given ICM of the rod. ICM equals to 1 over 12 MD square. So we can put here the value of IM plus IR, which is equal to MD square divided by 4 plus MD square divided by 12 times omega. Here we have L initial equals to L final. So D over 2 MV initial equals to MD square divided by 4 plus MD square divided by 12 omega. I want to calculate omega. So here we can omega equals to D M V initial divided by 2 times, we can put a common factor 12. Here we get 3 MD square plus MD square. 2 and 12, here we get 6. We put it up. So we get finally omega equals to 6 D MV initial divided by 3 MD square plus MD square. Here we can eliminate D and here square and square. So this is the value of omega of this system just after the collision. Part B determines the fractional loss in mechanical energy due to the collision. You know, in general, the fraction of energy, you know here about the mechanical energy, if you look well in the system, between the before the collision and just after the collision, we have the same potential energy. The height of the center of mass is the same between this point just before collision and just after collision. So we have H equal to 0. So mechanical energy is equal to kinetic energy only, plus 0 potential energy. Okay, when I say I want to calculate the fraction, it means I have to put the initial mechanical energy down. What is the loss in mechanical energy? It means delta mechanical energy absolute value. This is the loss in mechanical energy. The fraction must be equal to the loss of in mechanical energy divided the initial value of mechanical energy. Okay? So here you know the initial mechanical energy, which is equal to the initial kinetic energy. Initially, this one was at rest. We have only a translational kinetic energy of m, which is equal to m over 2 times v initial square. This is the initial one. At the now I want to calculate delta mechanical. Delta mechanical energy, because this one equals to delta mechanical divided by the mechanical energy initial. Delta mechanical absolute value. Okay. In general, to have a positive value, you can write here the initial, or anyway, you can say here, it's better, the loss in mechanical energy equals to the mechanical energy initial minus mechanical energy final. Okay? So here we have to put mechanical initial minus mechanical final divided by mechanical initial. Okay, this one is the mechanical initial. What about mechanical final? Which is equal, we have a pure rotational motion. So we have I over 2 omega square of the system just after the collision. We calculated already IS, which is equal to IS equals to 1 divided by 12 MD square plus MD square divided by 4. This is the value of IS divided by 2 times omega square. Omega square, here we have omega square, it means we have 36 times m square v initial square divided by 3 md plus md square. Okay, we can simplify this relation. You know this one, which is equal to 12 md square plus 3 m d square. Okay, divided by 12. We can eliminate this one and we put md square plus 3md square divided by 12. So we can put d out of the parentheses. We can put d here. Inside we get only one d, like this. We can eliminate this one and square from here. So we get here m final, m mechanical final, which is equal to 3m square times v initial square times d divided by 2 3md plus md. Okay, we have mechanical final, we have mechanical initial. We put here the value of mechanical initial minus mechanical final divided by mechanical initial, and we can calculate the fraction. You do the calculation here. You must have finally fraction equals to m divided by m plus 3m. This is the final answer of the calculation.